इस सेशन में हम करंट इलेक्ट्रिसिटी के ऊपर एक क्वेश्चन करेंगे जिसमें आपके बहुत सारे कॉन्सेप्ट्स क्लियर होने वाले हैं। आइए देखते हैं हमारा आज का क्वेश्चन। इन द डायग्राम शोन, दिस इज द डायग्राम, द नंबर ऑफ सक्सेसिवली एम्बेडेड इक्विलेटरल ट्रायंगल्स टेंड्स टू infinity. This is an equilateral triangle. Inside that triangle there is another equilateral triangle. Side length of this triangle is half the side length of original first triangle, and then inside this second triangle there is again an equilateral triangle. Inside that triangle there is another equilateral triangle, so on and so forth. There are infinite number of such embedded equilateral triangles. Every triangle has its side length half the preceding larger triangle. All triangles are made of same uniform wire having resistance lambda per meter length. All these triangles are made of same wire, and the wire has a resistance of lambda ohm per meter length. Side length of the outermost triangle is A. The side length of this outermost triangle is A. Find the equivalent resistance between the points A and B. You have to find equivalent resistance between A and B. Side length of the outermost triangle is A. Here there should be a full stop here, I am sorry, and this is capital F. Okay. So, find the equivalent resistance between points A and B. This is your question. I am getting out of the screen so that you can capture the question if you want to and give it a try. Okay. So, this is the circuit that has been given to us, and there are two key aspects that you must note if you want to solve this problem. What are those two key concepts? Let us first try to understand them. The first one is, if we assume that equivalent resistance between A and B is R naught, and if we remove the outer triangle, then the resistance of the remaining network about two vertices like R and Q will be R naught by 2. What am I saying? I am saying that if you assume that there is a battery connected over here and the resistance faced by the battery is R naught, that means equivalent resistance of this given circuit across points A and B is R naught. Let us assume that the R naught is the number that we are supposed to find. Then what I am saying is, suppose you remove this outer triangle, just remove it completely, and think that the circuit is now RQP, this point is P, RQP, and the triangles which are inside this particular triangle. So, you go on embedding triangles like this. So, the outermost triangle has been removed. If I do that, then equivalent resistance between these 2 points, if I connect a battery here, then this battery will face a resistance that will be equal to R naught by 2. What I intend to say is actually true for any circuit. Let me draw a simple circuit. Okay, let me draw a simple circuit. Let us say there are two resistances, 1 ohm and 2 ohm. You can easily calculate the equivalent resistance, it is 3 ohm. Now, if I double each and every resistance in a circuit, that means if I double this resistance to 2 ohm and I double the other resistance to 4 ohm. If you double the resistances given in a particular circuit, then the equivalent resistance just doubles. If you double the value of each and every resistance, then the equivalent resistance will double. The equivalent is 3 ohm, here the equivalent is 6 ohm. Similarly, if I half the value of each and every resistance in a given circuit, then the equivalent resistance will also half. This is very important thing. If you triple the value of each resistance in a given circuit, then the equivalent resistance will become 3 times. This is true for any circuit, any complex circuit, right? So, if you get this concept, then you must understand that if the equivalent between A and B is R naught, and if I just remove this outer triangle, then the circuit basically remains same because there are infinite number of embedded triangles. But what is happening, if resistance of this is R, then resistance of this side is, if resistance of this side is R, then resistance of this side or this side is R by 2. What it means? If I show a circuit like this to a student and tell him that this resistance is 1 ohm, this is 1 ohm, then he will understand that this is half ohm, this is half ohm, this is half, and this is 1/4 ohm, 1/4 ohm, so on and so forth, because resistance is proportional to length of the wire, and length of the wire is getting halved in each successive triangle. So, if I remove the outermost triangle, we are left with a circuit which looks like this only, but length of this side is half the length of this side. So, if resistance is 1 ohm here, then it will be half ohm here. If resistance of this side is half ohm, then resistance of this side will be 1/4 ohm. So, actually these two circuits are same, and there is one and only one difference. Here value of resistance is 1 ohm, then here it is half ohm. If here the value of resistance is half ohm, then here it is 1/4 ohm. If here the value of resistance is 1/4 ohm, then here it is 1/8 ohm, so on and so forth. So, actually the circuits are same because there are infinite number of triangles, but value of resistance in this particular circuit is exactly half of the corresponding resistance in this particular circuit. So, in a way, if you just remove this triangle, what you have done is you have created another circuit which is similar, but having values of resistances halved, right. So, if equivalent of this is R naught, then obviously equivalent of this across R and Q will be R naught by 2. So, this is the first key thing that you need to understand if you wish to solve this problem. The next important thing that we need to understand is junction at point P can be opened. This junction can be opened. This is another key important thing that you need to understand, and I assume that many of you have already done problems in which this concept is used. In fact, if you are watching my lectures, series of lectures on current electricity, I have considered such examples of false junction. Circuits where if junction is removed, it actually makes no difference. I will explain it in short here also. Suppose again assume that we connect a battery across A and B, right. Now, this circuit is basically symmetrical whether you look at it from this side A or you look at it from this side B, it appears exactly identical. So, if I naught is the current entering through A into the circuit, then same current I is getting out of the circuit at point B, isn't it? Suppose I is the current entering into the circuit at point A, this I will get divided into two parts. I do not know what exactly in what ratio. Let me assume that here the current becomes a small I. Okay. So, capital I minus a small I will go this way. Very good. Now, looking at the circuit from this side, I can say that current here will also be small I and current here will be I minus I. How can I say that? Because from this side and from this side, the circuit is exactly same. There is absolutely no difference. So, if there is a 2 ampere current in this resistance, then there will be 2 ampere current in this resistance as well. If there is 3 ampere current here, then there is going to be a 3 ampere current here also. Actually, positive charges are flowing like this. That is how we consider the flow of current. Positive charges are entering into the circuit from this side, and you can say that positive charges are coming out, or reverse it, you can say that negative charge, same quantity of negative charge is entering into the circuit from this side. So, if you consider it like this, that positive charges are entering from this terminal and negative charges are entering from this terminal, then it becomes absolutely clear. So, positive 5 coulomb charge enters, 2 coulomb goes this way, 3 coulomb goes this way. This is just an example, 5, 2 and 3 are just an example. So, negative 5 coulomb enters from here. So, obviously negative 2 coulomb will go there and negative 3 coulomb will go there because of symmetry. So, from this we can understand that current here is I and here also it is I. Interestingly, if I assume that current here is, I am just writing it I2, current here is I2, then please try to understand from the same logic current here will also be I2, because again these two resistances are symmetrically located whether you look it from side A or side B. When you look at it from side A, this resistance is in similar position as this one when you look at it from the side B. So if this current is I2, then here also current will be I2. Now look at this particular junction. What is happening here? A current I2 that is flowing here is just passing like this, and a current I that is going like this is just passing like this. So if I open this junction at this point, will it make any difference? If I just draw this circuit like this, opening this junction, then current I2 remains in this path, current I remains in this path. So actually it makes no difference to the circuit if I open that particular junction at point P. And this is the second important concept that we need to understand in order to be able to solve this problem. Now let us solve this